So you've done a lot of work with equations of lines, straight lines starting in grade 9, then in grade 10 you add quadratics, and then grade 11 and grade 12 you add all kinds of different curves, all kinds of different functions, but all of them in two space, right? Two-dimensional, typically the XY plane. And then all of a sudden, today we start thinking about, what about planes? If I'm in 3 space, I can have a line in 3 space. I can have a vector has a magnitude, right? So it usually starts at the origin and then goes only so far and then stops, and then also has direction. A line goes on forever in both directions. So a line would be like a function, if we think of it that way, right? So I have equations of lines. I have vectors. What about planes? So in 2 dimensions, xy is the plane. And all the points sit on that 2-dimensional plane. But in 3 dimensions, I can have different planes that exist with different orientations. I can have parallel planes. I can have planes that cross in a line. All different kinds of, which we'll get to, combinations and relationships between different planes or between planes and lines, that sort of thing. But how would you define a plane? So, and then I can picture the x, y, and z axes. And then if I just look at the x and y axis, that's a particular plane, right? But then, and that might be sort of like a standard plane. But I can have all kinds of other planes, like I said, that are skewed in that space. And so we need to have, just like we have equations for lines, we need to have some way of representing planes, of expressing different planes in 3 space. So that's what we're starting to explore today. Okay. So just for reference, this is standard form of an equation of a line, or and when we're working with vectors and in 2 space and 3 space, we call it the scalar equation. And so here's my line. And I have a normal to the line. And turns out normals are really important when we start talking about planes. And for this scalar equation in 2 space, a direction vector is negative BA. And if you think about the slope of the line, and if you think about the vector equations of the line and what a direction vector is, and by the way, I would recommend thinking about that. Like, I think that's kind of the point of what we're doing right now, is spending some time where you think about that. Why is it negative BA? Think about the slope. Think about those kinds of things. Right, like slope, rise, and run. And think about rearranging the scalar equation into y equals mx plus b. That sort of thing will allow you to do that. And if you go through that thinking, it will be easier to memorize all of these little details. Okay, so that's important. The direction vector. And then the normal vector, we can see once we have the direction vector that a normal to that vector would be AB. And if we look back at the previous unit and we talk about orthogonality and finding vectors that are orthogonal to other vectors, again, you can see why the normal vector would be positive A, positive B. So this is really important. If we've expressed an equation in scalar form, we can get its normal just by taking the coefficients of the x and the y. Okay. If we extend this into 3 space, we have a scalar equation of a plane. And again, I kind of just mentioned this, but I'm going to keep harping on it and add on to it. Taking the time right now, or as you're working, or just at some point if you're daydreaming, to visualize all of this is so important. Like, visualize why some of the things we say are true, and what a plane in space looks like and what its properties are like. We're talking about equations of planes today. We're going to spend a couple of days talking about properties of planes. And some of that will just be doing things with equations of planes. But here we're going to visualize a plane. Okay, and I have a normal to the plane that's at a right angle. And often, for some reason, for planes, we use pi to denote a plane, where we use a scripted L for a line. We often use pi. So when we think about the scalar equation of a line in 2 space, and its normal is just AB, for the scalar equation of a plane in 3 space, you can guess what the normal would be, and you'd be right. So it's easy, ABC. And there is no scalar equation of a line in 3 space. The scalar equation in 3 space is a plane. So there isn't a scalar equation of a line in 3 space. Definition of a plane. Now, this is a simple definition maybe. But I guess you could look at this as a difference between a straight line and a curved line. And at least in some circles, when people say line, they mean straight line. Okay, so you would either say a line or you would say a curve. But again, that kind of depends on the context, but some people argue about that as a formal definition. A line versus a curve, or a straight line versus a curved line, same thing. So a plane is like a line. A plane is a surface such that any straight line connecting 2 points in the plane lies entirely in the plane. And that's for all points and all lines kind of thing. So again, if I have a plane here, this is a plane. It's P, Q. And the line connecting PQ lies entirely in the plane. But that's only one example of 2 points. But you can picture, if the plane is a piece of paper, that it would be true for all points in the plane. Any pair of 2 points, there would be a straight line that would connect those 2 points that would lie entirely in the plane. You can kind of visualize that. So I'm going to attempt to draw one where that wouldn't be true. And you can draw it with me if you want. So what if I have this point P and this point Q? The straight line connecting them is not in the plane. It goes out of the plane, or not in that space. It goes out of it. Now, a curved surface like that is a thing in mathematics, and it's something that you can represent in other ways, and there's a whole area of mathematics devoted to this kind of thing. And actually, it's very interesting. I only know a little bit about it, but I know that I think it would be considered topology. And it talks about how shapes are similar or different based on their properties. So, for example, a mug would be the same as a donut because it's a three-dimensional figure that has a single hole in it. So mathematically, topologically, I think this is the case, they would be considered the same shape, even though to us, in terms of our use of them, they're totally different. But under that system, they would be considered the same shape. And so there's a whole branch of mathematics that studies this, and it turns out it's really important and useful in the real world. But it's obviously beyond what we're going to talk about. Does that make sense? Oh, this is why this looks kind of strange, because this should have an extra sort of line like that. then it looks a little bit more like a curved plane. But doesn't matter. Okay. To uniquely define a plane, we need either 3 points, and these 3 points need to be linearly independent. That means not at all collinear. So again, here's our visualization. I take 2 points. And I put a plane through those 2 points, but couldn't I spin that plane around like this? Right? Can you see that in your mind? 1 point here, 1 point here. There would be lots of planes that would pass through those 2 points. But once I pick one more point, that plane is fixed in a specific position. Unless the 3 points are collinear, then that wouldn't work. You'd need a separate point, right? So it's like you need a triangle of points to define a plane. Okay? Or 1 point and 2 vectors parallel to the plane. 1 point, obviously, in the plane. That kind of goes without saying. 2 vectors parallel to the plane. Again, we can move vectors around, so we don't think of a vector as being in the plane necessarily, but it's parallel to the plane. And a plane doesn't have direction the same way a vector has, right? So a vector could be parallel, but it could be parallel lots of ways in the plane. So you would have 2 vectors parallel to the plane. And if we have that, then we can basically create the equation. Okay. So now we're going to start doing some stuff. Given the scalar equation of the plane, determine if A and B are in the plane. Well, this is pretty simple. We're just going to do a left side, right side check. So left side is x plus 3y minus 2z minus 10, and right side is 0. So that's 1 plus 3 times 3 minus 2 times 0 minus 10. So 1 plus 9 minus 0 minus 10 is 0. Therefore, A is in the plane. Nothing interesting going on here. Nothing profound. So this left side is 2 plus 3 times negative 3 minus 2 times 4, minus 10, and the right side again is 0. Is that right? 2 minus 9 minus 8 minus 10, I think that works out to negative 25. Not equal to the right side. He is not in the plane. Determining if a point is or is not on a line in a plane, that's obviously an important thing, the kind of thing we like to do in mathematics. So quick example of that's one of the things we might be able to do, and you would have assumed that you could use a scalar equation in that way, and you sure can. Any questions so far? Okay, so we talked about the scalar equation of a plane. What about a vector equation of a plane? So our point, or our position vector, like it would be a point, but we would think of it as a vector when we're doing a vector equation. And we need two direction vectors, or two, that we don't call them direction vectors necessarily, but two vectors that are parallel to the plane, right? So plus S times D1 plus T times D2. So they would look something like that. And then a lot of the stuff that we're going to do some more interesting things today, but some of what we're going to do is just getting familiar with the notation, so converting between different forms. If you're given a couple of vectors and a point, can you write the equation? That's pretty easy because you're given exactly the information you need, but then, using that equation to change it to a different form, something like that. Those are the kinds of things, some of the kinds of things that we're going to be getting used to at first. Okay, any questions before we keep going? So example 2, find a vector and parametric equations for each plane. I'm given two vectors parallel to the plane. It doesn't say that, but we assume that it should say that. A and B are parallel to the plane, and it contains that point. But you remember from the learning goal today that, like, if you hadn't had some familiarity with this notation, it would be hard to just try to figure it out. Like, you need to know how to write the equations. You need to know how to write things. You need to know the kinds of things that you need. Okay, so I use the point P. Yep. Yes, sorry. I don't know why I wrote equals. And then for parametric equation, we get x equals y equals, this is where we break it up into its components, like this. So this one is, you just take the x part of each, right? So it's 0 plus s times 5 plus t times negative 2. So 5s minus 2t. 1 minus 3s plus 5t. And 5 plus 0s, so that's gone, so plus 7t. Question B gives us a point in the plane and then gives us two lines. Remember, those are lines. Those are not vectors, those two things that were given here and here. Those are equations of lines, but they're in vector form. And so the plane is parallel to those two lines. What does that tell us? Well, the direction vector in each of these, this should probably be a T. They're not the same S. The direction vector isn't necessarily on that line, but it's parallel to that line. It's the direction vector of that line. Remember, these lines would, you could think of it as starting at this point and then using the direction vector to find other points from there. Scalar multiple of that direction vector from a point just like slope, up 2 over 1, up 2 over 1. That's going to find all the other points, right? So it's similar to that idea. And it's parallel to these, so it's going to have, like, those direction vectors are useful, right? So I can use my point for my position vector for the vector equation of the plane as 4, 0, negative 6, the point that's in the plane, and direction vector 1 and direction vector 2 and then just write the equation. Don't fall into the trap that this seems simple, seems obvious, seems straightforward, but because some of it is so new, it's easy to forget the information you're being given in a question like this. What does it mean to be parallel to that line? You might guess. You know, if you're good at this kind of stuff and you have good intuition, you might guess and you'd get lucky because a lot of this stuff does kind of align with our intuition. But I'm telling you, if you don't kind of practice this and visualize and think about it, it can be easy to think this looks straightforward and simple, not practice, not really spend any more time thinking about it, and then all of a sudden find out like, ooh, actually, I don't really understand what information I'm being given that's relevant to this question. You know what I mean? Okay. Any questions? And then we could do the parametric. Why don't you go ahead and try that? Okay, that's what I got. Hopefully that's pretty straightforward. Not hard, but you got to know what parametric form of an equation means, and you got to get that separate from symmetric. If you were asked that on a test, and you're asked for one and you gave the wrong one or something like that, I mean, you're not getting any marks, right? Like, that part of the point is practice it enough so you know which one's which. All right, now we get into some slightly more interesting things, I think. This is giving us the 3 intercepts. We've never done anything like this. What do you think we should do? We don't have a point form, do we? Like, we talked about how 3 points defines a plane, but we don't have a form that just uses 3 points. But but I like your thinking. 3 points does define a plane. We have 3 points. What do you do? What do you do if you being asked a question you've never been asked before? Thank you. Sketch it. Yes. Let's draw it and visualize it. So that's usually our y. That's usually our z. And this is usually our x. So x-intercept is 2, so I'm going to go out 1, 2. I don't have a scale, but you know what I mean. So this is P 2, 0, 0. The y-intercept is 3, so I'm going to go out 3. That's a little bit further, and I'm going to call that Q 0, 3, 0. So intercepts are a little bit different, a little bit more interesting in 3 space because both x and z have to be 0 to be the y-intercept. And I'll call this one, oh, I don't know, how about r for 0, 0, 4. Now, how do we find the equation of this plane? What would we put in? And then what would that give us? Interesting idea. Elif? Okay, so this is a separate idea, right? Okay. So what Mason was saying, I'm curious, just to touch back on that, if we put in, we would get like 3 different equations and then have a whole bunch of unknowns that we would have to maybe start solving for or something like that. Would we have enough? Is there 4 unknowns? Would we have, I'm not sure if we would have quite enough in there to solve it, but that's an interesting idea. You'd have like a system of equations. That might be something that comes up, but Elif's idea is different. PQ would be a vector that would be parallel to the plane. And I have options here. I could use something else to come up with another vector, 2 other points, and then have a point. So let's take this route for now. I'm going to start with my position vector. Pick any one of these you want. And my first direction vector, if I chose PQ, now it doesn't matter what order you do because the direction of it won't matter. So if you get it backwards, this is still going to work. But if I do PQ, we subtract backwards, so that's actually Q minus P. So 0 minus 2 is negative 2. 3 minus 0 is 3. And 0 minus 0 is 0. So this was PQ. If you were asked to find the vector PQ and you got it backwards, that would be wrong. If you just have to come up with 2 direction vectors, it doesn't matter which direction you do. And then I'm going to use PR. So again, I subtract backwards. 0 minus 2 is negative 2. 0 minus 0 is 0. And 4 minus 0 is 4. So this is PR. That's just where they came from. So if I have 3 points, I can come up with 2 or 3, but I only need 2 direction vectors that are parallel to the plane that are not collinear, because that wouldn't work, right? They have to be sort of separate. And now I can write the equation. So go ahead and do that. Everybody okay with that? And then, yep, go ahead. Yes. Nope. So think of like, we kind of saw this the other day. Think of if you have equation of a line in grade 9 and you have the y-intercept, sorry, not the y-intercept, the slope, that's not in reduced form. Or think about, where do I have some space that I can do this? 2x plus 3y plus 4 equals 0, or 4x plus 6y plus 8 equals 0. Like those are the same equation, just one's not reduced. Now, it's not quite the same as being not reduced in this case, but it's sort of a similar idea. Okay. And in some cases, it could just be that it's not reduced. And in some cases, it's going to be useful for us to reduce. We're actually going to do that. Now, here's a big idea, big deal. Find the scalar equation of the plane in part C. Turns out this is a pretty important thing to be able to do, so you want to make sure you're paying attention, extra special attention to this one. Scalar equations are often the more useful form that we want. So if we have a different form, we're going to do some work and do some steps to put it in scalar form. All right. So where is it? There's the equation we had. How am I going to put this in scalar form? I wish I could ask a question like this without just showing you what to do, because it would be really neat to spend some time thinking through this and work through the process yourself of what you would do to get this. Anybody have any ideas? Want to guess? I mean, we only have a handful of tricks right now when we're talking vectors. What kinds of things can we do with vectors? John, what'd you say? Thank you. Okay. We're on the right track. Add, subtract, scalar multiplication. You said cross product, dot product. Those are some of the things we can do. What would help? Let's go back to the scalar equation. What else did I say turns out is really important about planes? Why? Ooh, that's an interesting thought. I like that. That's the right word. So if I have two, I like it. If I have two vectors that are parallel to that plane, when I take the cross product, I get a vector that's orthogonal. What do we call that? The normal. Why is the normal useful? Oh my gosh, because it's basically the equation. It's missing the d, but it's basically the equation. The normal vector is the coefficients of the x, y, and z. And if I have that, I don't know d, but then what could I do? Yeah, we have points on this plane. We can find points in planes. I could solve for d. Very nice. Hey, that was pretty good. We worked together for that one, but we did a pretty good job. So, we are going to find n. I wasn't joking when I said the normal is a really useful thing. Here's the problem with planes. This actually ties onto what Alof was asking. Hey, can't you have like different vectors defining a plane? Yeah, but a plane only has one normal. Well, maybe two if it goes the other direction, right? And scalar multiples of that, but you get my drift here, right? So there's an infinite number of vectors that are parallel to the plane, but there's kind of like one normal or something like that. So how are we going to find the normal? A cross B, where A and B are my direction vectors. So I'm going to go 3, 0, negative 2, 3, and 0, 4, negative 2, 0. Three times 4 is 12. 12 minus 0 is 12. 0 times negative 2 is 0 minus 4 times negative 2, so that's positive 8. And negative 2 times 0 is 0 minus negative 6 is positive 6. I'm actually going to call this Kn, and then I'm going to reduce it. And you get to decide what n is, because again, you can have scalar multiples. and you kind of have n in one direction or n in the other direction. For example, if I had done these in a different order, like I could do A cross B, B cross A, doesn't matter. Or if I had done RQ or QR, that's going to just change some of the positives and negatives slightly, but I'm going to get something more or less the same. So what can I do? I can divide each of these by 2, 6, 4, 3, and it just, if I have to use this, smaller numbers makes it a little bit easier. So I've got 6x plus 4y plus 3z. Don't forget plus d equals 0. Pick a point. So d should be negative 12. And then rewrite our equation in full. What do you think? Now we're getting into the good stuff. Now we're really starting to tie in some of the stuff from last unit and noticing, like thinking about the normal, orthogonality, and like I said, scalar equation of a plane is a good one. So we did some real work there to get it. All right, let's try a few different things that we can do. Find the intercept. That should say intercepts. I think we're supposed to find them all. Yikes, how are we going to do this? How am I going to find the intercepts in that? Like, where are the intercepts? What would be a better form to have for intercepts?
If we put it into the scalar equation and then we set the other two to 0, solve for the remaining variable.
Super easy at that point, right? So scalar equation is useful because I can sub in values for y and z, solve for x, and so on and so forth. So again, if I'm given vector form, we want to convert that to scalar form. So put, and you're going to notice, I think, a bit of a pattern, a bit of a trend, that very often, first thing we want to do is find scalar form. Okay, so I've got negative 3, 5, 2, negative 3, and 0, 6, 4, 0. So k times n is negative 18 minus 0. 20 minus 12, that's 5 times 4 minus 6 times 2. And 0 minus negative 12, so 12. I can divide all of those by 2, and then often we like the x coefficient to be positive, so I'm actually going to do negative 2, so I get 9, negative 4, and negative 6. That's not a rule that you have to do that. That's just a preferential thing. There's no magic to what k equals, folks. That's just like reducing to lowest terms to some kind of convenient form. Particularly if I had giant numbers, you can see that would be useful. I wouldn't want like 10 billion and 8 billion and 5 billion, right? Okay, so I can do this 9x minus 4y minus 6z plus d equals 0. How do I find d? Ayla? Thank you. We've got this position vector, which is a point in the plane. And that works out to d equals 17. Therefore, the scalar equation is 9x minus 4y minus 6z plus 17 equals 0. And now I can just basically state the intercepts. For the x-intercept, y and z are 0. So I'm going to move the 17 over. It becomes negative and divide by 9. So I get negative 17 over 9. The y-intercept will be negative 17 divided by negative 4. So 17 over 4. And the z-intercept will be 17 over 6. Everybody good? One more question here. Determine if the point is in the plane. There's not one way to do these questions. There are other ways to do them. What do you think we should do for this one? Yeah, so would that work? Could we check and see if both T and S are consistent? That might work. Yeah, or we could put it into scalar form and check left side, right side. And I mean, scalar form feels like it's a few steps, but it's probably a lot easier than coming up with parametric equations and solving for all of those ones. So I think we're going to go scalar form again. All right, so in this case, we've got 1, 4, 0, 1, and 5, 6, negative 1, 5. Go ahead and try that on your own. So I got negative 14, negative 4, 1, and I just flip the signs around. You can decide if that's worth your while or not. Maybe it's not. Don't forget that plus D. That's something that people get carried away and forget to do that and just leave it out. Yep. Say that again. Yeah? Because I multiplied through by negative 1, so that's a negative because it was positive there. Is that okay? Yeah. Okay. Okay, and what's our point? Our point is 4. It gives us that as the position vector in the equation. 2, 5, negative 3. And I believe this works out to D equals negative 51. And all of this was just to check if a silly little point is on the line, or in the plane, sorry. And that point was 4, negative 1, 1. Thank you. And it worked out. The point is in the plane.